So our next talk, we got 3 sessions all around BGP security and prefixes and things like this. This is near and dear to us here in this room because it's the resiliency of the networks that we build. Sharon's up first. This is a really interesting talk and kind of really looking forward to it. So let's pass this on to Sharon.
Okay, hi. I'm really pleased to be here to tell you guys about this work. This is joint work with a couple of colleagues. Pete Hammond, who's sitting right there, was a student at Princeton when we worked on this together. Michael Shapira is a postdoc at Yale and Berkeley, and Jennifer Rexford is a professor at Princeton. So what I want to talk about today is some issues related to the different secure routing protocols that people have been proposing over the years. I'm not here to propose a new protocol. I'm just going to look at the things that people have been talking about over the past 10 or 15 years and trying to evaluate which one is actually the right solution to use in the network. Okay? So when we talk about BGP security, what I'm going to be concerned with in this talk is a major sort of class of attraction attacks. We've seen these before. The Pakistan Telecom YouTube incident was one example when we had a black hole in the network. There was an ISP advertising a prefix it didn't own and was syncing all the traffic at their network. And so the traffic was actually just not reaching the destination. Another attack that has been considered, people have talked about the man-in-the-middle attacks. This showed up at DEF CON a couple of years ago by Pilosov and Capella. What happened here was you had an ISP that was attracting traffic through its own network and then delivering it to the destination. So no one can see that the attack was happening. It was actually, this ISP was able to eavesdrop on the traffic and nobody could tell. So all of these things have to do with attracting traffic by manipulating BGP messages, and that's what I'm going to be focused on today. We've been talking about BGP security for years, so we might think that if we had BGP security, all these problems go away. Right? But there are lots of different security protocols. They all work in different ways. They're all going to prevent attacks in different ways, and they all have vulnerabilities. So what I'm going to do in this work is we're going to look at the different protocols that people have proposed, try to understand how they work, what attacks work against them, and how effective they actually are in the network. So the protocols that I'm going to consider are origin authentication. Some people know them now as ROAS or RPKI. This is something that people are working on today. I'm going to call something defensive filtering. This is prefix lists. So keeping a list of IP addresses that your customers own and filtering announcements if they come for addresses that are not owned by them. I'm going through this very quickly. I'm going to give everything very clearly later. Okay, this is just the overview. And then, of course, our friends SBGP and SOBGP. So what we're going to do here is we're going to look at simulations of what these protocols would do if everyone in the Internet was to use them and attacks were actually being launched. So the way we're going to run these simulations is I have maps of what the Internet looks like. These are not our maps. These are other researchers who have produced these. It's the AS level graph of the Internet with the business relationships between the ASs. This was obtained by different groups, CADA, Cyclops. What we're going to do is we're going to use these maps and we're going to simulate what happens if all the ASs on the network were using BGP and these secure protocols and somebody launched an attack. Okay, so how can I predict how traffic flows in the Internet? So actually, I don't know what the routing policies people are using today in practice, and so all of the results that we're getting in this talk are within a very particular model of BGP routing policies that I'll tell you about next, based on business relationships. So basically, given this model, what we're going to do is we're going to look at what happens if everybody used these routing policies, and someone was to launch an attack when a particular secure protocol was being used, how effective would it be? Okay? So that's the overview, and I'm going to compare those different protocols that you can see on this slide. All right, so to start, what I want to do is run simulations to see how traffic's going to flow. But unfortunately, the Internet's complicated. We don't know exactly how people use their routing policies. So what we're going to do is we're going to use a model. Okay, so this is a model that's been used in many places before. It's not a perfect model, but it's the best one that I have at the moment. I would be very happy to hear from people in this room if they have suggestions on a better model to use. But I want to say that all the results we give in this paper are based on this model. So the model is, we're going to assume that there's 2 kinds of business relationships, customer to provider relationships. This is just where the customer pays the provider. And so in this graph that I'm showing here, whenever I have an arrow or something above something else, that's typically a customer-provider relationship. So I have here 3 customer-provider relationships. P2 is a customer of P3, and M is a customer of P2. Okay. And then a next kind of business relationship we're going to consider is settlement-free peering agreements. So in this case, no money is going to flow between 2 ASs. Right. So in this graph here, I've got 2 settlement-free peering agreements, one between P1 and V, and one between V and P3. Okay. So how are we going to assume that traffic flows? Well, what I'm going to assume in this model is that ASs are going to prefer cheaper paths if they can. So that means if they have a path through a customer, they're going to prefer that over a path through a peer, which they're going to prefer over a path through a provider. And in the case that they have to break a tie, then they're going to prefer the shortest path. Okay? So that's what the model looks like. So I'm going to just walk you through how traffic would flow in BGP. I'm sure that everyone in the room has seen this before, just to get the notation straight for the rest of this talk. Okay? So here's our prefix. In all of this work, we're going to assume that there's a single IP prefix. This is the one that's going to be hijacked. So in this figure, this IP prefix is owned by the victim ASV. And in order to advertise the prefix to the rest of the world, V is going to send a BGP message which just says its name and the prefix, right? So this is just the AS path. It's a path of length 1 with V in it. And then P1 and P3 are going to route to V. Okay, so as we continue through the network, P3 will put his name in the AS path and advertise the path to P2, and P2 will route to him. And finally, when we get to M is going to learn 2 possible paths, P2, P3, V, or P1, V. Now, both of these paths are provider paths, right? So they're equally expensive for him. So he's just going to pick the shortest one. Okay? So that's how routing happens in this network. And I want to actually mention that the graph I'm showing you here is an anonymized graph that I found inside the CADA data. I've taken out the AS numbers because I don't want anyone's AS to appear in this graph. Okay? But basically, this is just a graph that I found in there. So this is something that actually looks like this in the internet. So here's how traffic would flow. There's just one more piece to the model. And this is that someone is only going to transit traffic if it makes money. So basically, you're only going to transit traffic for your customers. Okay, this is a crucial aspect of the model. This makes sense because if the ASN was to advertise the path MP1V to P2, and P2 actually chose to route through it, then the ASM would be actually having to pay twice. It would be paying its provider to route the traffic forward and also paying P2 to carry its traffic, which doesn't really make sense. So in our model, we're going to assume that we're not going to have situations where nodes are carrying traffic for 2 ASs where neither one of them are a customer. Okay, so you're going to have to carry traffic only for your customers. Okay, so that's the routing model. And again, the reason we need this is because if I'm going to run simulations on how traffic flows, I need to know how traffic flows, right? So this is why this is here. Okay, so now we're ready to start talking about security. So I'm going to just start with a simple example of prefix hijacks on BGP. This is the kind of attack we seem to see in practice most often, or at least that people in the academic community know that's being seen in practice most often. So again, I'm using a graph from CADA's AS graph. We're going to use a single attacker and a single victim in this first part of the talk. So it's just a very particular graph I chose. The reason I chose it was so that I could illustrate all the things I want to illustrate. Later on, I'm going to show simulations which we ran over all ASs in the internet. This is just for illustrative purposes at this point. So we're going to work on this graph for the rest of the talk. And what I'm going to show here is we have a single attacker M. So imagine a router gets hijacked at this AS. And now he's going to advertise the prefix that he doesn't own. Okay? So now M is claiming that he's owning the prefix. So what's going to happen in our model? Let's first consider what happens with P1. He's got a customer link and a peer link, right? So the customer link is actually cheaper for him, and so he's going to prefer to route through his customer. That's what we're going to assume in our model. And if we continue, we look at P2, again, it's a customer route, and we consider what happens with P3. If P3 sees this announcement MP2 prefix, and also the announcement V, he doesn't know which destination is the legitimate destination, right? Because I'm assuming that there's no filtering, there's no ROAS, there's no nothing. This is just under the assumption that everyone's just using plain BGP with no corrections at all. So in this case, again, P3's learned 2 announcements. One of them is through his customer, which is P2. The other one is through his peer, which is V. Even though the P2 path is longer and it's false, he's still going to prefer it because it's a customer path. Okay? So when I talk about attacks on BGP, I'm going to assume that nobody's using any kind of route filtering at all. The reason we're doing this is so that we can compare what happens when we have a security protocol versus when we have nothing, when we have some other security protocol. Okay? So this example assumes no filtering. All right, so what's interesting here is that if we look at the attacker, what I did was we ran simulations of this attack with this particular set of ASs on the entire AS graph. And we measured the number of ASs that actually ended up routing through the attacker. And so it turns out that 62% of ASs in this AS graph will route through this attacker. And if we look at this graph, it seems kind of surprising. The reason that this attacker is very successful is because it's a stub, sort of at the edge of the internet. If everyone's preferring customers, it looks very attractive, especially if the victim is higher up in the internet hierarchy. Okay? So that's an attack on BGP. And if we had ROAs, all of this would go away. This attack wouldn't happen, right? So what I want to do now is consider, I'm going to talk about what a ROA is, and then I'm going to show whether or not we could still have an attack with ROAs. So the previous attack wouldn't happen. Why? Because what origin authentication is, or what ROAs do, is they're basically, in terms of functionality, okay, let's not worry about implementation for now, let's just look at functionality. What they're doing is they're giving us a secure database that maps between IP prefixes and the ASs that own them. Right? So if we had some kind of secure system that tells us who owns what, then we can't have these manipulators announcing paths to prefixes that they don't own. Right? So that last thing we saw couldn't succeed, and this attack wouldn't happen. But now, what happens if this attacker was a little more clever, and he wasn't just fat-fingering the wrong IP address, he was actually launching an attack? Okay. So there's a very simple thing he can do. Now, instead of just claiming that he owns the prefix, he can claim that he's connected to the guy who owns the prefix, right? So what I'm showing here is that M is announcing the path MV prefix. He's connected to the victim AS. And if we look at what happens again with P1, he's still got a customer path through the manipulator, and he's got a path to the victim. But the path to the victim is the peer path, so it's less preferred than the customer path. And so even though this path is longer and it doesn't exist, he's still going to choose it. Same thing we saw before. So again, if I look at P3, again, P3 has two paths, one of them through P2 and one of them through the victim. The victim's path is shorter, but it's a peer path, which is less preferred than a customer path, right? And so he's going to prefer to route through the attacker. Okay. So this is just a very simple way that someone can just manipulate ROAs by just announcing paths that are shorter and don't really exist in the network. What's interesting about this, again, in this example, before I showed you that he got 62% of ASs in the internet, now when he's restricted to using, when there's ROAs in the network and he has to announce connections to the victim, he's attracting 58% of ASs. So basically he's about as successful as he was before. Okay. So, you know, I think looking at this, we can all agree that announcing paths that don't exist in the internet are probably things that we don't want people to do, right? So there's been protocols proposed to deal with these kinds of attacks. These protocols are SBGP and SOBGP. These two protocols are slightly different. They have different security properties. I'm not going to go into the details of why they're different or what they are unless we have questions afterwards. For the purpose of this talk, I just want to look at secure BGP. The point of secure BGP is to prevent people announcing paths that don't exist in the network. And the question is, we'd think, and what I thought actually when I started this work is if we had secure BGP, we don't have any more attacks, right? What I want to show you is actually there's still a way to manipulate the system even if you have secure BGP. So what secure BGP does is it's going to give us origin authentication. So it first has this mapping between IP prefixes and their owners, just like as before. So just like what the ROA functionality would give you. But also they have the ability to prevent an AS from announcing paths that were not announced to it. Okay, so the way they work, the way SBGP works, is it uses public key crypto. It's this property, this functionality called a signature. So for those who don't know, what a signature does is there's a public key infrastructure, so anyone can get the public key of someone else from this infrastructure. And if a message came from V, and I have V's public key, I can verify that that message really came from V and not from someone who's pretending to be V. Okay? That's what public key crypto gives you. And so what secure BGP does basically is we build up this infrastructure of public keys, and it's an inline protocol. What networks are going to do now is instead of announcing BGP messages in the clear, they're actually going to assign their announcements. So what I'm showing here is V is sending the path as before, V prefix, and he's sending it to P1, and then he signs that whole message. So that yellow bubble around the thing is the signature. The signature covers all those things. Okay, so the protocol looks just like as before, except now whenever someone says something, they have to sign it. So in this example here, what P1 is going to do is when he puts in his announcement, he's going to sign it with his green key and also include the previous guy's signature, which is the yellow key, right? And so the announcements actually have these lists of attestations. So for instance, if we look at what's coming out of P2, P2 is going to announce to M his own path, P2, P3, V, and prefix, and also include the announcements of the previous two other guys, each signed by their key. So now anyone can grab the key from the public key infrastructure and verify that these messages came from the people that said they came from. Right? So what we saw before was someone making up a link in the network that wasn't there. This couldn't happen, right? Because what would have happened here is that M would have needed a message from V saying, M, here you go, M, here is a path V prefix that you can use to advertise to your neighbors. And there's no such message in this graph, and so that attack wouldn't have happened. Okay? So secure BGP prevents all that from happening. But Okay, so he's going to choose the path as before. So routing just happens as before. It's just a different format for the messages. Okay, so that's fine. So now we can no longer have paths that are announced that don't exist in the network, but what can still happen? So sometimes this is known as a route leak. We can still have something that looks kind of like a route leak, okay? So what's going to happen here is P1. So what M is going to do here is he wants to attract traffic from his neighbors. He can no longer make up paths, right? So he can just advertise paths that are really there. So what I have him do here is he's going to pick the shortest path he has, which is through P1, and he's going to advertise that, right? And this is a valid secure BGP message, right? He signed it with his red key. He's included the signatures from the guys before it. Everything looks great, right? So he announces this valid message. We look at P2. What is P2 going to do? Well, P2 has got the option of two messages. One is through P3, which is 2 hops long, and one is through M. Now, if we look here, if P2 wasn't using any sort of filtering, he would just prefer his customer path, right? M is his customer, P3 is his provider, M is cheaper and more preferred. And so if this guy wasn't implementing his filtering properly, he would still route through the attacker. And similarly, P3, which is even further away through the attacker, doesn't really know necessarily what the attacker is. He might see this message and see, oh, this is a customer path to the prefix I want to go to. Great. I prefer customer. I'm going to route to this. Okay? So we can still have route leaks even with secure BGP. And the reason for that is because people can prefer customers, okay, in this model. So here's something interesting. When we look at this, when I ran the simulation here, we found that he attracts 16% of the internet. And I know that many people in this room are going to say this is not an attack. I'm not here to tell you if it is an attack or isn't an attack. What I'm here to talk about is that it attracts traffic. Okay? This is a good way to attract traffic if you're a stub. Okay? So we can talk a little bit more after, and I'm happy to take questions, and I'm interested to hear actually what you guys think about this type of thing. But the point is that it's quite effective. Okay? So before I go on, this quick interlude. How much time do I have? Okay, I have 20 minutes. Okay, so this is a very quick interlude. This is just a little bit of a technical point that might be good for this community to know. Again, something that surprised us when we did this research. What's the best attack strategy, right? If I'm an attacker, how should I attract the most amount of traffic to my network? Okay, so people's preferences typically based on AS path length, right? So we'd think that an attacker, he can't really make up business relationships. He can't change the local pref of his neighbors. He doesn't control that, right? But what does he control? He controls his path length. And so we would think that the best way to attract traffic to yourself, if you're an attacker, is just to announce the shortest path you could. Right? And that's actually what we ran in the simulations. This particular attack, attracting the shortest amount, announcing the shortest path you can. Okay? It turns out actually that this is not the best attack. Sometimes we have really weird things where announcing the shortest path is not the best thing to do. Sometimes announcing a different path that's even longer is actually better. The other thing you would think is that if I want to attract the maximum amount of traffic, I should tell the path to as many people as possible. That seems to make sense. Again, things with BGP never make sense exactly how you'd expect them to. So sometimes announcing to fewer people is better. So we have examples of both of these, and I have a paper that I'm happy to talk about after that we show that this is the case. So there are cases where announcing paths that are longer is actually better than shorter. This is a technical point. What we found is it's actually hard to find the optimal attack strategy. It's hard to compute, if you were an attacker, what's the best way to attract traffic to yourself. So the reason I'm bringing up the point to this audience is that just to know that these attacks are complicated, it's not really possible to predict what the worst possible thing can be. And in particular, what we did in this paper was we simulated what we considered a bad attack, which was this attack of announcing shortest paths to as many people. But I emphasize that this is not the optimal attack. Sometimes there are worse attacks, okay? But this is what I'm simulating in this paper. Okay, so now just to quickly show you why would a longer path be better, okay? So I'm going to show you why on the example we've been talking about. Okay, let's look at our attacker. Before he had, oh no, okay. So actually, my animation broke. So actually what I showed before was the attacker was announcing the path through P1. Okay, because that was a shorter path. The P2 path is 3 hops long, the P1 path is 2 hops long, so it's better, right? Okay, let's see what happens if he announces the longer path through P2. So what he's going to do is he's going to, as before, set up his secure BGP announcement as usual with his signatures and everyone else's signatures and announce that to P1. And P1 is going to send traffic to him because he prefers customer. Okay, this is exactly what I showed before, only on the other side. Okay. So actually, it turns out that he gets 56% of the internet if he does this. When I use the shorter path, he gets 16% of the internet. So you can see that actually announcing a longer path is better than announcing a shorter path. And in fact, it's almost as bad as the original prefix hijack I showed you in the first slide. So 62% of the internet went through him for the prefix hijack. With this strange long path secure BGP route leak, he's actually attracting more traffic. I guess I'll... Okay, so while he's setting up, I'll just quickly make this point. Why does this happen? Okay, let's look at that AS. P1 has 500 neighbors. P2 has 4 neighbors. Okay, so the trick is to attract the bigger guy. Right, P1 is bigger than P2. So the point that I'm trying to make with this is that these attacks are complicated, and sometimes, you know, the most obvious thing is not really the right thing that the attacker will do. Yeah, question.
So it seems as if to attack, you want to. Sorry, I'm Jeff Sachs from Blue Ridge Networks. So it seems as if what you want to do is to purchase transit or to purchase.
Yeah. Yeah, so you want to attract
ISP service from a lot of different providers, and have one or two of them be very close to the core, but then announce in different directions your path through the other ones, so that no matter whom you're talking to, the other party sees it as advantageous to transit through you because you pay them.
Right. So let me just to clarify the point. The point here is that I picked one path, the 2-hop path, and announced it on one side, and then I picked the 3-hop path and announced it on the other. The point made was you could pick both paths and announce them on both sides and see if you can get more traffic that way. That is a valid point. The only thing about secure BGP is that we would hope that it would have some sort of expiration time on the messages. And so at some point, if I'm announcing to P1 that I'm routing through P2, I'd no longer have the announcement from P1 that I can send over to P2. Right, so I'd lose the ability to produce that announcement because the expiry would go off. So that's why I considered this kind of attack, rather than having it announced on both sides. If you had no expiry, this is certainly something that could happen, which is probably why we need an expiry. Okay, I'm going to go on from this point. So we had here a stub, right? Our attacker was a stub. In practice, many providers use prefix lists, which is an excellent thing, and I'll tell you in a second why. So in this paper, we considered the following kind of prefix lists. I realize that there are different ways that people do this in practice, and I actually love to hear about how you do it. So if you find me afterwards, tell me exactly how you do this. I would love to know. But this is what we assumed in this paper. Assume that providers know who their customers are and which customers are stubs. So a stub is an AS with no customers. Okay, so it's an AS, has no customers. I'm its provider. I know that this guy is a stub. And I'm going to also keep a list of the IP addresses that is owned by this AS, by the prefix. The prefix is owned by this AS. So basically what I'm going to do as the provider is if I see an announcement from the stub that is not for a prefix that it owns, I'm going to filter that announcement. I'm going to drop those announcements. So those who are familiar with the Pakistan YouTube attack, Pakistan Telecom was not a stub, but if its provider had noticed it was advertising a prefix that it doesn't typically originate, then that attack wouldn't have happened, right? But in this case, I'm only considering stubs. Okay, so let's assume that this is what every provider in the internet was doing. So let's imagine a perfect world in which this was happening. In this example here, what would happen to our attacker? Okay, P1, as soon as it sees this announcement from M, it's going to say, wait a minute, this prefix is not in the prefix list for M, and I'm just going to ignore this announcement. And again, the animation broke, but what would happen is that P1 would actually route correctly to the victim rather than to the attacker, and this attack would be completely eliminated. Okay? So now why is this useful? It turns out that when you look at maps of the internet, 85% of the internet is stubs, according to CADA and Cyclops data. So if all of their providers were to actually filter their routing announcements and only allow them to announce paths for prefixes that they own, then 85% of traffic attraction by stubs would be eliminated. Okay, and we're going to see in a second that this is very useful. So that's the end of part one. We've gone over all the different protocols that we considered and what could happen with them. Now we focused on a single example. The reason is because this was a cool example where I could show you everything I wanted to show you. But now let's consider what happens on the internet as a whole. So what I'm going to do here is we're going to take random pairs of attackers and victims. So ideally, I would have liked to have every AS be an attacker, every AS be a victim, and run n-squared attacks. But that's just too many. So I just sampled at random. Okay, so what we did was we took a random attacker, random victim, and let's just define for now, for the purpose of this slide, we'll say an attacker is successful if 10% of the ASs in the internet route through him. Okay? That's the success metric, at least for this graph. In a second, I'll get rid of that. But just for this graph, 10% of the internet routes through the attacker is successful. So what I'm going to do, we're going to count how many pairs of attackers and victims where the attacker is successful if he launches these attacks on each of the protocols. So if we look at BGP, the first yellow line, it's about 90%. So what that means is for 90% of attacker and victim pairs, when you choose them at random, the attacker attracts at least 10% of the internet. Okay? If we look at secure BGP and secure origin BGP, the first point is that they look just about the same. Very, very, very slight difference. Okay? It turns out that that metric goes from 90% to about 12%. So only 12% of attacker and victim pairs manage to attract 10% of the internet. That's what those bars mean. Okay. So what I think is most interesting here is I can't actually point, but if you look at the purple bar under BGP, that is about 12%. What is that purple bar? That's under the assumption that every provider in the internet does filtering in the way I described. So filters its stubs. Okay, so kept prefix lists for its stubs and stopped announcements from stubs when they announce things for prefixes they don't own. What happens here is for only 12% of attacker victim pairs, the attacker manages to get 10% of the internet. And this looks just about like what happens with secure BGP. Okay? So the point here to take away from this graph is that if everybody filters, we get a benefit that's basically as good by these metrics as secure BGP. Okay? That's not completely the end of the story, but I just want to make the point in this graph that these things are very comparable. The numbers are comparable, but what they're doing is totally different. Okay, so what prefix lists are doing is they're eliminating attacks by stubs. Since only 15% of ASs in the internet are not stubs, those are the only ones that are left to attack in this analysis. Okay, so that basically what I'm showing is the purple bars are the yellow bars scaled down to 15% approximately. Okay, so that's the first point. The next point is, okay, I have time, good. So the next point I want to make is that remember that this strategy underestimates damage, right? So this was the particular strategy where I pick the shortest path and announce it to as many people as possible. The shortest path I can get away with and announce it to as many people as possible. I said before that things could be worse. What we do know is with filtering, 15% of attacks, only 15% of attacks can get through with filtering. So this black line is a hard line for those purple bars, where these yellow lines potentially can go over the bars. So it's unclear if there are even better attacks possible with secure BGP. We couldn't find them because it's hard to simulate all of them. Okay, so that's what this data is telling you. Now, so the point is, though, that secure BGP is not a replacement for filtering. It's actually, we need both in combination. So again, if we look finally at that small purple bar far at the end of the graph, what that's showing is if we have a combination of both secure BGP and filtering, okay? So what happens is the way to look at this graph is secure BGP drops the percentage of attacks by about 10% to fraction of 10, 1 over 10, and filtering drops it by another fraction of 1 over 10. So when you have a combination, it's about 1 or 2% of attacks are getting through, okay? Because we're stopping the attacks by stubs and we're forcing everybody else to announce paths that actually exist. So the only attacks that can get through are non-stubs that are advertising too broadly, basically. They're carrying traffic from one provider to the other. That's what that purple bar is showing you. So there's very few attacks left. Okay. The other thing is that you might ask how valid are these results. We ran these simulations over 2 different AS graphs. I just wanted to show you how well they agree. This is actually very surprising for us. It turns out that they agree extremely well. So what I'm showing you here, let me just flash this. This is the 2 different data sets. The curves looks just about the same. Okay. What this graph is showing you here was before I was focused on the attacker attracting 10% of the internet. That's that horizontal line that you can see over there. This graph just shows you for all possible amounts of traffic the manipulator has to attack. So for example, if you draw a horizontal line up from 4%, from 40.4 on the x-axis, sorry I don't have a pointer, that's the attacker being successful if he attracts 40% of the internet. Okay? The horizontal line is the attacker being successful if he attracts 10% of the internet. So the takeaway point from this graph is that if we look at SOBGP and SBGP, first of all, that's the red triangle and the green upside down triangle, those curves are basically on top of each other. Okay, so at least on average, these things are doing about the same thing. The other thing to notice is that if we look at this defensive filtering curve, so this is what happens when you have just plain BGP and prefix lists, that's the blue squares. It's very similar, again, to secure BGP and secure origin BGP. Okay, the curve looks different because it's a different thing. different set of attacks that are being prevented, but on average, it looks just about the same. Okay, so we're getting about the same benefit from these things. Okay, so the thing is, though, if we have defensive filtering, we still have potential attacks from the higher level ASs. So if the only thing we're filtering are stub customers, if you are an attacker and you want to launch an attack, you're no longer going to launch an attack from a stub, you're going to launch it from a bigger AS. Okay, so do we still need to worry about this? So here's a graph that's very similar to the previous graph I showed you. What I'm doing here is we're going to consider what happens when the attacker is not a stub, so that's the blue line there, has at least 25 customers, so we can think of that as a tier 2, and at least 250 customers. So that's a huge AS in the data that we had. And what we see is, what we would think is if you're trying to attract traffic, who's going to get the most traffic, right? The tier 1s, right? No, actually not true. Turns out that the tier 2s get more traffic in this model. The reason for that, tier 1s are at the top of the customer provider hierarchy, so if you want to route through them, you have to pay, whereas tier 2s are the customers of the large tier 1s. So it turns out when we ran these simulations, tier 2s actually end up attracting the most traffic, and this is an absolute, this is not relative. And the reason is because they're basically the customers of the tier 1s, and if they launch the attacks, the tier 1s will prefer them, and the most amount of traffic will go through them. So you can see that on this graph because the green line, which is the tier 2s, is above the tier 1s, which is the red line, right, which is pretty low. Okay. So the point is that, yes, even if we have defensive filtering, we still have potential attacks by the tier 2s, and the way to slow these down is to use secure BGP. This is attacks on plain BGP. If we had secure BGP, these curves look a lot better. They're a lot lower. Okay. So bottom line, so if I can leave you with a couple of points. Secure BGP and all these different protocols that we've been looking at over the years, the cryptographic protocols constrain the paths that you announce. And that's really important for limiting the amount of traffic a manipulator can attract. However, it does not constrain the export policies. And so if you're an AS that wants to attract traffic and you're in a world where there's secure BGP, what you're going to do is announce the path as broadly as possible in a way that's possibly unexpected. So if you're hijacking someone's router, you might announce the path to more people than your actual sort of host network would have announced it to. And the combination of the two things, filtering and SBGP, is important. So we would get really far if everyone was to filter today, we would get really, really far. We wouldn't get far enough, but we would get very far. The way to think about it is that these cryptographic protocols are preventing path shortening attacks, but we still have route leaks with them. One way to prevent route leaks is to use filtering, but if we only filter, then we don't prevent path shortening attacks, right? So these are two different attack vectors that we've seen and two different ways to prevent them. Just a final thought, how are we going to actually implement filtering? So it would be great if everyone filtered properly, so I can stand here in front of all the operators in North America and say, please filter properly. So if you did, it would be great. Here are some suggestions. The implementation is imperfect. Why? Because it relies on altruism. So I'm running a network. I'm supposed to filter my customers to prevent the rest of the internet from being attacked. It's possible that there are some providers that don't have enough clue to do this properly, or maybe they just don't have the resources to invest in it, right? So if we're going to assume that everyone uses filtering, what this trust model essentially amounts to is me assuming that every provider on the internet has a clue and is honestly implementing filtering. And that's hard to do. But one way to actually get closer to that is to notice that keeping prefix lists right now is difficult, right? So how are you going to keep track of exactly what prefixes your customers own? Here's an observation. We're looking at deploying ROAS and the RPKI, which is going to be a mapping between ASs and their IP prefixes. So why not use the ROAS as input to your prefix lists to figure out which prefixes are actually owned by your customers and use them for filtering. So that's basically my final thought, something to work towards. And in the meantime, basically using prefix lists as well as you could will prevent a lot of these attacks. So, last thing. Okay, we have some small providers. Imagine you're a small provider, you don't have the resources to do filtering, okay? The question that I wanted to answer with this graph is, if the small providers, which we can't really rely on to do filtering, don't filter, how bad does it get? So what we need to consider is, if you're an attacker, you're going to get your announcement out to the world through the smallest provider, the weakest link, the one who doesn't filter, okay? So which fraction of stubs can actually get things out if providers with less than 5 customers don't filter? That's that red triangle in the pie there. Okay, so what this pie is showing, if the providers with less than 5 customers don't filter, then about 14% of stubs are still able to leak their routes into the internet. That's what this graph shows. If only the providers, the huge providers with more than 500 customers filter, then 14% of stubs cannot leak their traffic to the internet, but the rest of the network can. So the bottom line is, if we had ASs with at least 10 customers all filtering, if we could make that assumption, then 56% of stubs could no longer leak routes into the internet, which would really, limit a lot of the prefix hijacks that we could see. And this is just to show you that the two data sets are agreeing on these numbers. Okay, if you want full details, there's a tech report on my website. This paper is going to appear at SIGCOM in August, and if you have any questions or any suggestions on how to improve this, please let me know. Thank you.
We have some time for questions. Please say who you are.
Hi. Hello. Todd Underwood, Google. So I really enjoyed the first part of your presentation. The second part seems wildly optimistic, to say the very, very least.
Okay.
If you assume that all large customers with Clue prefix filter, then we can get good results. But if we assume good things are true, then often good things are true. That turns out just not to be true, and not only not to be true, but not to be possible after years of bellyaching by lots of people in this room. It's just the ability of people of the size of, say, level 3 to create an accurate prefix list for their transitive downstreams, their customers that are changing on a moment-by-moment basis, just turns out to not be possible in the current setup. So we can either create a brand new network that's incompatible and is a massive transition. Wait, we did that, V6. Okay, good, so it's going to be all set. So I guess what I'm saying is it seems wildly optimistic to rely on any form of prefix filtering to solve this problem.
Okay. Just to that point, you were talking about filtering the transitive customers. Actually, I didn't make that assumption in this work. So we're only assuming that you're going to filter your direct customers. I'm wondering if you think that makes a difference.
It's the same thing. The routes I received from my direct customers, they got from their customers. So either I break them as a provider.
No. Okay, so I think my assumption wasn't clear. Okay. So what I'm assuming is that I'm going to have, if my customer is a stub, then I'm going to filter it. If it's not a stub, I won't filter it. That's what this analysis assumed. Okay? So basically, I have multiple customers. Some of them actually have their own customers. In that case, I won't filter them. But for the customers of mine that are stubs, I do know what prefixes they originate. They should only be originating prefixes. If they're doing anything other than originating the prefixes that I know they're supposed to have, then I filter them. Okay? But any other AS that has multiple customers of its own, I'm not going to filter.
That is actually a useful simplifying assumption.
Okay. And by the way, this plot here is this is sort of the way to think about what happens if only the big guys do it. So the blue triangle at the top corner is if you only had really huge ASs that we would expect to be able to filter stubs, if they were to do the filtering. This number, 55% of attacks, is when the AS has at least 10 customers. So.
And just to clarify on this slide, when you say 55% of attacks stopped, you mean 55% of the possible places attacks could be sourced or eliminated, right?
Yes.
So we could have exactly as many attacks originating from the remaining 45%.
That's correct. Yes.
Sandy Murphy, Sparta. I've been trying to figure out something about the attacks from stubs. In the model that you presented, the only reason why what M was doing was considered an attack is that M was a stub.
Yes.
So if M was, UUNet and was passing propagating the route through itself, that would not be an attack.
No, sorry,
Right.
that was misunderstood.
No.
So actually that would be, so in the model that we used, what we assumed was that every AS is only going to transit traffic if one of the sides that it's transiting for is a customer. So if it was UUNet or, I don't know, someone, he wouldn't carry traffic, let's say, from Sprint over to UUNet, even if he's not a stub. Our model would assume that that was an attack.
Right. So so the whole reason for considering it an attack is because he's a stub, and that's an aspect of the business relationship that he has with various people.
Yes.
Okay, so along the lines of the manipulator getting around origin authentication by lying about the existence of an edge in the graph, suppose he just lies about his business relationship and says, oh, I'm not a stub. I have this business relationship with this other company. You can expect to see routes propagate through me for that, so
Yes.
don't bother putting filters in space. I'm not a stub.
Right. Okay. So that is something that would. Okay. So just to distinguish 2 points. First of all, if the filtering model that I used, what you suggested would attack the filtering model that I used, right? So if I'm supposed to know who's a stub and filter only if it's a stub, then a good way to attack me is to lie to me and tell me you're not a stub. Right, so that's correct. I just want to make clear that we assume that sort of transiting traffic for people that aren't your customers is unusual behavior and would only be done in the form of one of these traffic attraction strategies.
Right, which is good if it's an accident, but if you're being deliberate about things, no reason to presume that you're being honest as well.
Right.
Right? Okay. All right. Thank you.
Danny McPherson. So I'm glad you did this work, actually. I think people have been saying this for a long time. I mean, even recently, a lot of things with the route leaks and whatnot in particular. If you look at like Jared's route leak page, for example, the anomalies that occur, in the routing system, every single day, hundreds of them sometimes are route leaks. And that's, so any of those could be malicious. So I'm glad you did that piece. On the prefix filtering side, I was at Internet MCI in '95, and we prefix filtered every customer and every nested transit AS, and people stopped doing that. And some of the reasons they stopped doing it were because things like BGP route refresh didn't exist, and incrementally updatable prefix filters didn't exist, and that sort of thing. And I don't think those excuses are there anymore today. And I think that ISPs should be fully obligated to prefix filter all customers, and I agree with your recommendation of generating those both based on ROAs and and using that with on the ingress side of for any transit AS. So anyway, I'm glad you qualified and quantified this, and I pretty much agree with everything you said. So just want to make sure.
Heather would be the last question.
Heather Schiller, Verizon Business, former UUNet. So it sounds like you make your definition of stub an organization that doesn't transit for an external entity?
Yes.
Okay. So I think it's a little bit of what Sandy said, that it's an incorrect assumption because you can have a provider who has a customer that does not have their own ASN that allows their provider to announce with their own ASN.
Okay.
And so you can't, as a provider higher up, it's hard to validate the relationship that your direct customer has with any of their downstream customers.
And those guys are not actually making BGP announcements, the downstream customers.
Correct.
Okay.
So, for example, an ISP could connect to UUNet. That ISP could have static customers that don't do BGP, that don't have an ASN, but have PI space. And it's really hard. And this kind of gets into the prefix filtering problems, aside from the RPKI and ROA stuff that maybe will help it, but maybe will not. It's really hard based on RIR data to validate those relationships, or to even know that an organization exists behind your directly connected customer when you have nothing else to verify against. So that's, yes, prefix filtering is an ideal, but it's really hard to verify those relationships when there's no database of that information to go and check against, what those relationships are. The other thing that I wanted to say is that it seems like in most of your presentation, you make the assumption that garnering the largest percentage of traffic is the goal.
Yes.
And that may not always be the case.
I agree.
If you want to only divert a small portion of the traffic, targeted to intercept some portion of it, it may not be at all necessary to make waves and grab the largest portion of it.
Right.
A very targeted, looking at who connects to who, where can I, get a route in to just take off a portion of the traffic that I'm particularly interested in, and could do it undetected, relatively undetected if folks aren't paying attention. And so I think that that's something that's important to keep in mind, because that's a larger, not a larger, but it is as important of a security concern.
Right, I agree. So just to both points, the first point that you made, actually, maybe after, if we have time, people could sort of talk about what the RPKI world is doing about that issue, because I feel like it's the same problem. And to the second point about, not knowing if people are running targeted attacks, I agree that's absolutely important. What we were trying to do here was just really macro and trying to figure out where are the vulnerable points in the internet. So if you were to actually try to do a study of, how could you launch a targeted attack? We have simulators that you can use, perhaps if you're interested in those studies, but we didn't at all do this in this work.
So, as someone who's also on the AARON Advisory Council, I think that it's important if other operators in the room have similar problems verifying prefix list information to sort of say, hey, RIRs, please do something better or different, or if you have an idea about how it could be done differently, to kind of match like prefixes in organizations, because the processes that exist today allow companies like Go, Verizon Business to have, numerous accounts and org IDs, and it's very hard to correlate all of that information just using the database alone if you don't inherently know a lot about the organization. So it's extremely difficult to do that for your ISP type customers.
Okay, yeah, Heather was going to be the last one. So I encourage.
I got one quick comment, which I think it's important, is the only thing that's changed is if we have RPKI and ROAs, you don't have that excuse anymore, and those route origin authorizations exist, and you can use that to bootstrap whatever prefix policy you want, and that's the thing that's changed, and that's why people should look at employing that information for prefix filtering.
Right, and we'll have a talk here in a few minutes on RPKI with that. So I'd like to thank Sharon. If you haven't met her yet, come up and after the talks and look her up and find her and stuff like that.